Hello everyone, it's August 12th. Alright, what do we have here? Lowest common ancestor of a binary tree. Given binary search tree, find the lowest common ancestor node of two given nodes. The lowest common ancestor is defined between two nodes. Haven't we done something similar? That's not a binary search tree. Yeah, I believe we have done this for the regular tree. So I'll do it as a regular tree. Lowest node in T that has both as descendants. P is 2 and A should be 6. 2 and 4 should be 2. Yeah, how do we do this? I don't remember. Well, if we want to find the 2, so what we need to do is whether this one exists. Yeah, remember that's how it is. So like, given myself, I check in my left subtree if they exist, in my right subtree if it exists. So the situation is 1 1 0 1 1 0 or 0 0, and I return this value because I have 2, right? I have 2, so I have 4 different situations. So when we check for 1, and we'll eventually on this, the first time that we get it, then we shall set. What do we return? A tree node. Okay. Yeah, I don't remember. Maybe binary search tree does have some property that can make this one easier. It's possible. Oh, binary search tree is just the left node is smaller and the right node is bigger. So if we're given 6, so I know 2 must be on the left side, 4 must be on the left side. So immediately it's not going to be 6. If I immediately know it's going to be on 1 on this side or 1 on this side, then immediately it's myself, right? Because it's on either side, I must be the lowest common ancestor. But if they're on one side and I do on this one, and then for each one I check the 2 values. Whenever the 2 values are stripped on both sides, then that one will be. So I'll solve this like this. Common ancestor. Don't return anything. Just say self.res. None. And this one also don't return anything. So we say if node, if p.val, and all of these are unique, right? Smaller than node.val, node. That's it. Aleph node.val is it is a P and Q. just they're not the same. If p dot val is larger than q dot val, swap them. So p not always a smaller one, q always a larger one. So if this is larger than q dot val, then DFS no dot left. And DFS no dot right. And we call DFS on root. Oh, and what if it's equal? If it's equal to any of them, then we shall return. So maybe I can do this. Right? The smaller one is equal, the larger one is larger. The larger one is equal, the smaller one is smaller. Yeah. Let's see. Yep, seems to be working. Yep, it's working. That's why it's simpler. Using the method of as if the tree is a regular binary tree. However, tree being BST means that we can use additional info contained in the values to simplify the search process. Whenever a node sits between the P and Q values, the node must be the lowest common ancestor. I'll say it's login and take a peek. I hope the test case doubles. Is it today's solution? 128. 27th. Just added one more. Oh yeah, this is another one. That's true. Is number of matching. It has to be 2. Match the left, match the right. The number matching the left, number matching the right. If it's 2 and it's none, we set it. Yeah, that's the regular solution. That's what we're thinking about. Oh yeah, this one's a little easier. Just say P is this and Q. They're both smaller. Doesn't go left. Both larger. Alright. Otherwise A here. You don't even have to. Or just do 2. Oh, this is simpler. Exactly, it's simpler. Alright. But it doesn't really matter too much. Call it. Alright, so yesterday we timed out, which I think we can improve by adding a parameter. We can say self dot first available row, called front, is 0, right? And then every time when I call, and then we will say, if it's this, then no, the front doesn't change. Otherwise, we have the index, right? Whoa, hold on. It will fill. Gather will not change the index, because not change the front, because gather will try to find a row that fits. So gather is find a maximum row, and we're going to fit it, right? So it will change every time we call scatter, because scatter we go row by row, and otherwise index equal to, actually that's not index. That's not index, man. We start with front. So right, and then I think all these index is going to be self dot front. And then we just keep incrementing the front. And of course here, when you search, it's not search 0, it's self dot front. It's front to maximum row. So before that, everything will be maximum. And of course, every time we call, we say if this, right? And say if max row is smaller than self dot front, also return. It's not possible. This is the same. If max row is smaller than self dot front, return false. And the total empty is going to be, because we cannot do the front, so we're going to be the query this minus self dot bit dot query self dot front. So front is defined as the front minus 1. So the maximum of this. Actually there. If self front margin 0. So this is 0. So yeah, front should be the first row that has empty seats. And Theta will go up, so it has to be smaller than 0. Alright, let's try this one. By incrementing the front, hope is that we'll make things, we do make it faster, but we're also causing mistakes. This is the case, this is the way to go, but we're making a mistake, which we don't want to. This is the test case. Let's go back to the original test case. Ah, shoot, it's correct. Oh man, I need a good test case for this. Let's go through this logic again. If the front is larger equal to k, okay? Then we'll take k away, update this position with that many. This one update this position minus k, so we just minus k, and then k minus equal to k. Which is brilliant. But we also did a self.front plus 1. Which is true. Well, which is actually not true because because after this, the front might not keep going up. And we can escape here. We can jump out or we can temp equals to this. It's smaller than k. This one set to 0. This, this, and then k minus equal this, and then front plus equal 1. Makes sense, right? Which means this one shall hide inside. And then we can just break here because it's fine. It's okay. We can just break here. Or so we just filled up the entire thing. So this is what I change. I'll break here and I'll increment inside, because if it's larger then we don't have to increment anymore. Now front my point into an empty one, I agree. So let's add one more. We'll just say, actually we can add here, right? Once you break out, we need to make sure the frontal is pointed to the first and then empty. Just say while self.empty seats self.front. If it's equal to 0, then self.front plus equal 1. Just walk into the first one. So this one must be right. Now I'm going to try this one. That's the one. Front smaller than len self.empty seats and silly of me for forgetting this. One row 2. This will work. This will work. Oh no. What? Oh yes. Oh yes, man, yes. Yes. What a Hercules effort to get this one to pass. Holy moly. This is bonkers. Maximum. Quickly query the max value. So this is the max value segment tree. Sum binary indexed tree. Right? And this is first row that still has empty seats. This one, binary search to locate the smallest row that has at least target a number of seats. find the current smallest row that has empty seats. Nice. Hercules effort. But this is a good question. So, my original intuition was correct. This problem can be solved by a max segment tree and a segment tree, binary search, and a sum segment tree which is implemented via binary index tree. The only additional optimization, the max segment tree is used for gather, whereas the BIT is used for scatter. The only additional optimization is to record current smallest row that has empty seats, which this significantly shrinks the search space as more gather calls are made. So I would say it's a log n query, but binary search is also log n. So O2 log n for each gather. Call it O n because k has to. We gotta move forward front. Let's say O r log n for each scatter, where r is max row. Okay, what is the hint? Good hints. That's a good problem. Oh, look at this. There are better ways to make the tree, I guess. How? Oh, you can build two in one? Well, technically you can. You can build two trees in one. Yeah, that is true. Hmm. Might have to use another to make a pass. Yeah, I don't want to. Still pass without any tree. Is that brute force? Really? Oh, hold on. This can also do a segment tree. Maybe something we can read. Eh, that'll be it. I mean, nothing more to say. If in production code, probably need to, I don't know, check a few things. Profile it. It's always profile it. Alright, see you guys tomorrow. Adios.